laptop got overheated, so I have to split this recording. We are in part F. So we are trying to find the total potential energy of the system of the three charges. Um, so to do that, we are going to we have this. I wrote this equation before my laptop had issues. To find the total potential energy of the system, I add the potential energy of each pair of the charges. So U total is the total potentials, and then U1 is U2 and U3 is the separate potential energies of the system of the three charges. So we're gonna do the distance between Q1 we know and Q2 is A, and then the distance between Q1 and 3 is 2A as right here, and then the distance between Q2 and Q3 is 3A. So we're gonna do is we're gonna write, so we know that U, so just U like alone is going to be K times Q1 times Q2 divided by R. So that is the equation we're working with. So let's go ahead and form it. Okay, let me just write this down. Okay. So for Q1, we're going to do Q, K, MK times Q. I don't know why it's different. My laptop is freezing again. K times Q. Okay, so we need K times Q1. So Q1, remember Q1 is positive E, and then Q2 is negative E, and then Q3 is negative E. So we're gonna write that down. Q1 is equals to positive E, Q2 and Q3 are both negative E. I believe that's how it is. Yes. Okay. Let's form it. Form the equation. Okay. Q1 and Q2 over the distance A, and then here is going to be K Q Q1 and Q2 over the distance is 2. Just double check. I meant Q1 and Q3, sorry. Q1 and Q3. So let me write it down so it's less confusing. Q1 and Q3 over R, and then the next one's gonna be KQ 2 and Q2 over R. So that's gonna be K negative E order over the distance 3A. So we're gonna start. This is gonna be negative KE 1A. I'm gonna put 1 because it will be easier for the next step. Negative KE squared. Oh, I forgot to put squared at top. Squared over 2A, and then positive KE squared because negative, and then squared on 3A. There we go. Okay, so now I'm gonna just remove this out of the way so I can continue my calculations. Okay. So now what we're gonna do is we're gonna add these all together. So I'm gonna factor everything out of KE squared and over A. We're gonna factor that. And then negative 1 plus negative 1 half, and then this is gonna be 1/3 plus 1/3 because we're basically factoring them out. So now we're gonna make them common denominators. So we're gonna make them as 6. This is gonna be 3/6, and this is gonna be 2/6. Total, we're gonna add them together. This is 5. This is 6. And this is gonna give me -7, I believe. Yes, -7 over 6. So now the u total equals to ke squared over a times -7 over 6. This is going to be -7 ke squared over 6a. Now we have to do the k, and I don't know if you guys remember, but k is equals to 1 over 4 pi, what do you call this again? I forgot. This is what do you call this? Forgot. I think epsilon not a. Epsilon. Okay. So now I'm gonna do that. So I'm gonna check out -7 e squared, taking the k out so it's easier, multiplying that by 1 4 pi epsilon not. Okay. So that's gonna give us -7 e squared over 6 times 4 is 24 pi epsilon not. Okay. So that is gonna be the total, the potential total, potential total energy of the system that they choose. Now we're gonna do is part G. So for part G, I'm gonna go ahead and draw the diagram. Let's do that. Let me read the question first. A point charge Q1 equals to 5.00 positive nano coulomb is at the fixed position of x equal to 0, y equals to 0, and z equal to. You find that you must do 8.10 times 10 to the power of -6 joules of work to bring a second point charge from infinity to the position of x equals to positive 4.4 centimeters, 4 centimeters, y equals to 0, z equals to 0. What is the value of the second charge? So I'm gonna go ahead and make the diagram. So for this diagram, you're gonna have to make the y and the x-axis. So let's do that. Just that. Okay. Make a line. Okay. X and y. Okay. So we're going to. Oops. This is gonna be the 5. So this is the 5 nanocoulombs. This is the Q1 basically. Q1 equals to 5 nanocoulombs. And it is 0, 0, 0, x is 0, y is 0, z is 0 as well. This one is Q2. This one we don't know, and we're trying to find the value. This one is 4, 0, 0. So the distance between the two is r. We're going to do r1 equals to what is the distance between them? 4 centimeters. 4 centimeters. Yes, this is going to be 4 centimeters. Of course, because this is from 0 and then this is to 4, so it's going to go 4 centimeters. So we are doing part G, so I'm going to label it here, part G. So what we're trying to do is we are trying to find the value of the second charge. So I placed the Q1 at the origin, and then I put the Q2 over there. So the distance between them is 4 centimeters, and so I'm going to convert the 4 centimeters into meters by, I think, dividing it by 100. So I think maybe 0.0400 meters. The equation requires meters. And since the second charge starts at infinity, its initial electric potential energy is 0. So the work done to bring the charge in is equal to the final electric potential energy. So work is equal to U. Work is equal to the U is the potential energy. So the equation for the electric potential energy is U equals to K Q1 Q2 over, I believe this is R. Yes, distance R. So we are trying to find Q2, so we have to separate it. So to do that, we're going to remove this R, turn it to the other side. That's gonna give us U times R. And then the denominator gonna go back up, and then here is multiplying, so we're gonna have to divide it. So it's gonna be KQ1 in the denominator. So now what we're gonna do is we're gonna work with numerator and the denominator of that. So U times R separately, and then we're gonna do K times Q1 separately. So let's do that. So we already know the values. So we're gonna go ahead and write that. To the U is equal to work, and the work over here it shows in the problem. You find that you must do 8.10 times 10 to the negative 6 joules of work to bring a second point charge. So we're gonna use that 8.10 times 10 negative 6 joules. And we're multiplying it by Q1, and we know what Q1 is. It's I mean not Q1, I meant R. R is distance, and we know what R is. It's 4 centimeters, but we convert it into meters. And then now we're going to do K times Q1, and we know what K is. It's the constant. So 8.99 times 10 to the power of 9, and Q1 is 5.00 nanos coulombs. And we're gonna convert that to regular coulombs. And to do that, we can basically just do 5.00 and just multiplying it by 10 to the power of negative 9. Now we're gonna multiply these two, and I'm gonna put in my calculator. And I got 3.24 times 10 to the power of negative 7. And for the second one, the denominator, I got 4.95. Now we're going to divide these based off of this equation, obviously. So the numerator divided by the denominator, let's put that in the calculator. And I got 7.208 times 10 negative 9. So we are going to round it to 7.21 times 10 negative 9 coulombs. Or the answer can be 7.21 coulombs. So that's the answer. So sorry, I made a mistake. That's not W. I meant to put Q2. So now we know what Q2 is. The second charge, the value is 7.21 nanocoulombs. Then now what we're going to do is part H, the final. So for part H, let's read the question. Once the second charge is in place, how much additional work would you have to do to bring the third point charge Q3 equals to positive 2.00 nanocoulombs from infinity to the position of x equals to 0, y equals to 3 centimeters, positive centimeters, and z equals to 0. So now that we know what Q is, Q2 is the second charge, we're just gonna write it down, which was 7.21. Now we know that. Now we have to try to find the third point charge. not the third point charge. I meant um, the how much additional work would you have to bring the third point charge. That's what I meant. So let's put the third point charge up here. And the third point charge that we read was positive 2 nanocoulombs, and the distance between these two would be, we're gonna name this R2, and obviously 5 minus 2 is 3 centimeters, and it also showed us here y is equal to 3 centimeters. So this is Q3. This is equals to 2 equals, and the 0, 3 centimeters, 0. So 0, x equals to 0, y is equal to 3 centimeters, and z is equal to 0 as well. So now this is like, if you notice, this is 4 by 3, so this is gonna be definitely be a the R3, the third distance is definitely gonna be 5 centimeters, and this is because it's if you do 3 squared plus 4 squared, it's gonna give us 25, and that's gonna give us 5. Oops, that's gonna give us 5 centimeters. So that's gonna give us 5 centimeters regardless. So it's definitely a 3 by 4 by 5 right triangle. Yeah, the 3 by 4 triangle. So what were I trying to say? Hold on. So so what we are trying to do is, we since the third charge starts from infinity, the initial electric potential energy is 0 as well. The work required to bring it equals the total of the electric potential energy between Q3 and the two other charges that we already know. So we're gonna go ahead and write down the equation that we would be working with, which would be work equals to Q1 Q3, divide that by R2 distance, K constant, Q2 charge, the second charge, and the third charge over the third distance. So that's what work is going to equal to. Based off. So I'm just going to write down all the given that we have, so it's easier to work with in the equation. So this is the nanocoulomb converted to coulombs for the first point charge. Now this is the second point charge and the third point charge. 7.21, we found that in the last part. Coulombs, 2.00 times 10 negative 9 coulomb, which we just found out for this in this part. And then for R2 and R3, it's 3 centimeters, so we're going to convert it to meters for this problem. So we're going to divide it by 100, so 0.0300 meters in centimeters, and 5 centimeters is going to be 0.0500 meters. So we're going to go ahead and form the problems. So let's do that. So K, we always know K is going to be 8.99 times 10 to the power of 9. The first point charge, we wrote it down. Q1 is 5.5 coulomb. Multiply that by Q3. This is going to be 2.00 times 10 negative 9 coulomb, all the way divided by the distance R2, which is 0.0300 meters. I'm gonna go ahead and make this smaller so I can fit the page. Okay, now we're gonna do add second one. 8.99 times 10, 9. Q2 is 7.21 times, that's the second point charge. This is 7.21 times 10 to the power of negative 9 coulombs. And let me make this smaller. There we go. You'll be able to see. Okay. And Q3 is the third point charge we just found out in this part of 2.0010 negative 9 coulombs. We all divide that over R3 distance, which was 5 centimeters, but we turned it into meters, so 0.0500 meters. And we're just gonna plug everything into the calculator. And so I got 3, I got 3, so I got answer 2.5927, but we're gonna round it, so it's gonna be 3.00 times, and it says e to the power of negative 6, so 10 to the power of negative 6 joules. Add, and then for the second answer, I got, oh yeah, I meant, hold on. So for this answer, the first one, I got 2.99666 e negative 6. So I rounded it to 3.00 times 10 to the power of negative 6 joules. And then for the second one, I got 2.5927. So I'm gonna round. I'm not gonna round it. I'm gonna keep it like that and round it in the end. There are 9. Hold on. 9. We're gonna round it 3 here. Times is e negative 6, same thing, joules. And now we're gonna add both of them, and I got 5.589. So let's round it to 5.59. In e negative 6 times 10 to the power of negative 6 joules. And so that is what. So basically the work equals to 5.59 times 10 to the power of negative 6 joules. Since all 3 charges are positive, they repel each other, so positive work is required to bring the third charge into the system. Therefore, that is my answer. Thank you.